So we were talking about Gauss-Markov theorem. uh, Gauss-Markov theorem talks about statistical properties of the OLS estimators. So what we are discussing here are the statistical properties of the OLS estimators. The theorem says that given the assumptions of the classical linear regression model, the OLS estimators in the class of unbiased linear estimators have minimum variance, that is, they are blue. Where B stands for best, L stands for linear, U stands for unbiased, E stands for estimators. So the estimators are blue, that means they are best, linear, unbiased.
Excuse me,
Est-
sir.
yeah,
Sir, can you please summarize a bit from the starting of the Gauss-Markov theorem? Gauss-Markov theorem.
yeah. I will be talking about these only, but I just explain uh, before explaining each part of it, the gist of it.
Okay, sir.
So, so of course I'll be explaining each and every part of it.
Okay,
So
sir.
best linear unbiased estimators is what the Gauss-Markov theorem tells us, that given the assumptions, right? Given the assumptions uh, of CLRM, given that you are using OLS, given these two things, if you calculate beta 1 hat and beta 2 hat, which are the estimators, Gauss-Markov theorem tells us that these estimators are best. Best estimators. It tells us that these estimators are linear. It tells us that these estimators are unbiased. So you can say that these estimators are blue. That means they are best linear unbiased estimators, right? So let us talk about the individual point. There are 3 points to discuss: 1, 2, and 3. We discussed yesterday about the first point, linearity. We discussed about unbiasedness. Of course, we need proofs, proofs for all these three, right? There has to be a mathematical proof. This is just a statement of the end result, right? So OLS estimators are linear, OLS estimators are unbiased. What is the meaning of linearity? You know it. What is the meaning of unbiasedness? I explained yesterday. It's a one-liner. Expected value of beta 2 hat is equal to beta 2, and expected value of beta 1 hat is equal to beta 1. This is called unbiasedness, right? Now, today I'll discuss the third point. Third point says that the estimators have minimum variance. Minimum variance means that now when you're saying minimum, we have to understand the meaning of minimum. So there has to be some numbers: 2, 2, 5, 10, 1, 3. Then only you can say which one is minimum. So 1 is minimum out of these, right? So when we are saying minimum variance, then we have to compare some variances, right? So where are you going to compare? You're going to compare other estimators. So this is suppose OLS estimator. It has a variance of 1. And these are non-OLS estimators. These are all non-OLS estimators. Right? So among all the, and these are all not only non-OLS, but they are also linear and unbiased. Linear and unbiased. All of these are linear and unbiased. Linear and unbiased. Linear and unbiased. Linear and unbiased. So all these estimators have these variances written as numbers 2, 2, 5, 10, 1, 3. So these are the variances of a group of estimators. All of them are linear and unbiased. One is OLS and all others are non-OLS. So among the class of all linear unbiased estimators, the OLS estimator is not only linear and unbiased, it is also efficient, means it also has minimum variance, right? So when we were discussing now, why do we want to have minimum variance? You can connect it with the discussion that we had yesterday. We were talking about when we are happy. We are happy if this variance is low, right? We were happy when this is low, isn't it? Because that makes beta 2 more precise, right? So if we want to have precision, we want our variance and standard errors to be low. We discussed it yesterday. So you can connect it. We want it to be low. And this is talking about minimum variance. So we want to have, I mean, there can be other estimators and they would be having some variance. Then among all linear unbiased estimators, the one that has the minimum variance would be the best, right? That's why this adjective best in blue, B stands for best. Which one is the best? Among all linear and unbiased estimators, which one has minimum variance? That would be the best. And it is the OLS estimator that has minimum variance. Again, you need to prove it. It needs a proof. This is just a statement of what needs to be proved mathematically, right? So that's what this third property talks about. And this is a graphical explanation of the third property, that suppose beta 2 is OLS estimator and suppose beta 2 star is non-OLS estimator. This is OLS estimator and this is non-OLS estimator. This is the sampling distribution of beta 2 and this is the sampling distribution of beta 2 star. We have drawn we have put all the values of all the samples that are possible from a given population of a given size, and then we have drawn a density function. Some sort of density function has been fitted, and we got a sampling distribution, a probability distribution of two estimators. One is OLS estimator beta 2 hat, which we know, and some other non-OLS estimator, which is here. And if we compare them in this graph, compare beta 2 hat and beta 2 star. If you compare them, you would see that beta 2 hat has smaller variance. You can see the distribution. This is smaller than this one. It has higher variance, right? And this one has lower variance, right? So, of course, both are unbiased because you can see that the mean, we know the mean of the normal distribution is in the center. So the mean of the distribution, which you can say uh, is expectation of beta 2 hat is also here, and mean coincides. That means mean of the sampling distribution is equal to the mean of the true population parameter in all the three cases. But that means OLS estimator has is unbiased. Non-OLS estimator is also unbiased, but OLS estimator has lower variance as compared to non-OLS estimator. So OLS estimator is best, right? So this is graphically explaining what does efficiency mean, right? So this is efficiency property. This is efficiency property of the OLS estimator. So Gauss-Markov theorem talks about
Sir,
three
actually,
things.
somebody is trying to join in.
So Gauss-Markov theorem talks about three things, and these three things are linearity, unbiasedness, and efficiency, right? So now if you have any question, you can ask. Otherwise, we will move forward to another slide. Any question? Priyank, any question?
No, sir, understood.
All right. So let us move forward. And can you see the screen? PowerPoint.
Yes, sir.
All right. So this is something called goodness of fit. Goodness of fit, as the phrase itself suggests, that it means how good we are fitting a line to our scatter. How good is the line? How good is the fit of the line to the scatter? This is the question that we are asking when we are talking about goodness of fit, right? How good is the fit of the line? If the line fits the data well, the goodness of fit is good or very good. Sometimes it's not that much good. Sometimes is uh, is bad. So although you will be fitting the line using OLS, so what you get using OLS is a line which fits the data. Next question you ask, how good is the fit of the line to the scatter? And then you assign a numerical value to this variable. I'm saying it a variable. So it's a variable. It can be good, it can be bad. The fit can be good, the fit can be bad. So we assign a numerical value to it, and that numerical value is known as coefficient of determination. Coefficient of determination, which is written here. We call it R squared. R squared. R squared. Right? R squared is a value that measures goodness of fit. Right? So now if all the observations fall on the line, then R square is 1 and goodness of fit is 100%. Right? If the line fits the data very well, then R square is very high, close to 1, right? Of course, 1 is 100%, so it would be less than 100%, so it would be say 0.9, right? Or 0.8. So this is good fit. This is close to perfect fit, right? So we are happy when we have this sort of fit. Something R square close to 90% or above 80% is very good. So that we will say, okay, we have fitted a very good line to the data. So my SRF or my sample regression line fits the data very well, right? Uh, why do we want to have a good fit? Because if our line is fitting the data very well and R square is close to 1 or say 90%, 95%, then it means that our residuals are small. Our residuals are small numbers, right? And when these residuals are small numbers, then we would say that summation ui hat squared is low, right? And when summation ui hat squared is low, then because this thing appears in the standard error formula, standard error equals to sigma divided by summation xi squared, and this sigma is equal to summation ui hat squared divided by n minus 2, so that in effect this quantity summation ui hat squared enters into the numerator of standard error formula, and when the numerator is low, standard error is low, and then we have more precision. So we are happy. So we need to have our goodness of fit close to 1. It can be between 0 and 1. R squared can be between 0 and 1. That's the range. And it measures goodness of fit. So let us see how to calculate R squared. How do we get it? Now you might be thinking that when we fitted the regression line, I said that this is the best line. When we use the OLS, we want to have the best line in this scatter. And then we used OLS. And then we fitted a line that passes through the points. And we said that using OLS, the least squares principle, we are able to fit the best line, best fitting line. So when we said that we have already fitted the best line, then why are we talking about goodness of fit? Right?
Yes, sir.
Is it the question in your mind?
Yes, sir.
Okay. Any explanation? Is it contradictory?
Sir, maybe we are trying to find the goodness of fit to actually examine, uh, or to like revalidate our results whether our line of best fit is actually the line of best fit or not.
Okay, but when we were talking about OLS, I said that this line is unique, right?
Yeah, sir. So I want to say maybe we just want to check its uniqueness or whether it is
Mm.
actually a unique line or not.
No, no,
Like
it
it's
is a
just a guess.
unique line. There is no doubt about this that when you use OLS and you fit a line to a scatter, when you fit a line to a scatter using OLS, you will get the best possible line so that that line is unique and there is no other line that you can fit which is better than that. That's the end of it. So that's what OLS does, right? So we already got the best fitting line to this data. And now we are talking about goodness of fit, right? Seems to be contradictory, but it is not. It is not contradictory. It seems to be contradictory, but this statement is fine because the reason is if I say that Priyank is the best student of the class, it doesn't mean that Priyank is good. So if I'm trying to check the goodness of Priyank on some parameters, and if I'm saying that Priyank is the best student in the class, it doesn't mean, or let us say Priyank is the best student in the world. Even then, it doesn't mean that Priyank is good. Priyank may be the best, but he may not be good. Do you understand?
Uh, e- no, you are saying that I am best in the class, but I'm not best in the population. Is this
No,
what?
no, 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 no. I'm saying that uh, what is the best that you can do? What is the best that you can do? But even when you're doing your best, that may not be good enough,
All right,
right?
all right. Okay, okay. So you are. Oh, oh, got it, got it, got it, got it, got it. For example, some we are saying that this is the tastiest food that has ever been cooked, and the food is not the it's not the most tasty food of the world, but it's the best we can actually foresee. But there is a chance of improvement. You're trying to say that. I got it.
No, no, no.
Okay.
You are coming to the point, but still, I am not able. I think I'm not able to explain it with a good example. Okay, so let us say, okay, let me take the regression example. So this is the data. We fit a line to it, right? And this is the best line that I have drawn here. This is the best that you can do. OLS has done it. And you are sure that this is the best you can do. OLS has given us the best line. And this is the line, right? Now suppose now there is another data set, and now you have fitted a line. OLS has again given us the best line for this data. But in this case, r squared is 0.9, but here r squared is 0.5. Both are best lines that can be fitted to the data, right? So OLS has given the unique best line that can be fitted in both the cases, case A and case B. But in one case, r squared is 0.9 in case A, and in case B, r squared is 0.5. So don't you think that even though you have got the best line, there is a need to check the goodness of it,
Yes, sir, understood.
right? So that's the point here, that we must understand that once we have got the best line using OLS, then again we are talking about goodness of fit. What's the point? It means that we did not get the good line. This is a this is a wrong line of thinking, and there is no contradiction, because there is a need of calculating r squared, because ultimately if you want to know how good is the line, how good the line is fitting to the data, you need to have some measure of it. Sometimes the best line may not be equivalent to good fit, right? All right, so let us see mathematically how to compute r squared. So are you familiar with this equation?
Yes, sir.
All right, so I'll come back to it. I don't want to confuse you here. Again, here also, let us leave it. I need to explain it on my own without using these equations. Then I'll come to the equations, right? All right, let me explain here. Don't look at the equations, just see what I am saying. So I'm drawing a graph. This is the line. This is yi. This is y hat. And this is y bar. So this is y bar. This is a given x value, and this is the corresponding y value. So there is this x and y combination that gave us this point, right? So you are familiar with this graph. I don't need to explain it that much because you know it very well. Uh, so let me mark the. Let me ask you, what is ui hat? Yi minus yi hat. Do you agree with this? You have to say yes, no, so that I move forward.
Yes, sir.
All others, I want to hear from others also. Do you agree with this? Just see the graph. You can see where is the ui hat, the vertical distance. Let me draw it from here to here is ui hat. So do you agree? Do you remember this residual? What is a residual? That's the definition of a residual,
Yes, sir.
right? Now, what about uh, So, all right. So the explain, I mean, in this graph, we start with the mean, remember. Mean is the best model, right? So if you have data, what is the mean? If this is the mean, y bar, then y bar is one number, say 5, y bar equals to 5, that explains the data. So this is a summary of the y data, right? So you have y data here. If you want to say something about y, you will calculate the mean. You will say y bar equals to 5. So 5 is a measure of all y's, right? So mean is the model to start with. Then we are doing regression, right? Why we are doing regression? Why? We want to improve over the mean. We want to do better than the mean, right? Mean is not everything, right? So we want to do better than the mean. Mean is okay. Mean tells us about what are the values of y. It summarizes y in one number. But we want to do better than the mean. We want to drive deep into y and just say something more about y. And we want to talk about associations also, so that we have a x also, and we want to bring x into the picture, and we want to say how much x affects y. So we do a regression, and the motive of regression is to do is to do something better than the mean. So for to bring about to bring improvement, we do a regression. And when we are doing regression, we are looking at this quantity from here to here, right? So we got a measure y bar, a measure y bar, and a measure of y's, right? Y bar is a measure of y's. And see the distance between y bar and y. What is the distance? See, mean is far away from the actual value, but mean represents that actual value, right? Mean is representative. Y bar is representing yi. Y bar is representing yi. But there is a difference between yi and y bar. Yi minus y bar, right? So how do you explain this? That's the question. Regression answers this question. Regression answers the question that why the difference, what happens to the difference between yi and y bar? Because y bar represents yi, and there's a huge difference between yi and y bar, which you can see in the graph in orange. This is yi minus y bar, right? So regression tries to find the answer to this question. Are you getting? In plain words, I'm saying, I'm not talking about any of the math here. Just look at the graph and try and understand what I'm saying. We are trying to make sense of this difference. Why the difference? Yi minus y bar, although y bar is representing yi, right? So it will be difficult for me to start from zero and explain this again. So please pay attention and please ask if you have any question in mind on any of my point, right? So don't sit back at this point, because if you tell me, sir, please explain again, I will explain again, but I'll sort of move fast, right? So Did you get this difference? Yi minus y bar, the meaning of this expression yi minus y bar. What is this? This is, let me,
So yi minus y bar is basically the difference between the actual value and the mean value, right?
yes, yes, yes. And why why are we interested in this difference? So I told you that explanation. We are interested in this difference because y bar represents yi, and because y bar is a representative of yi, then this difference has to be, we have to talk about this difference and we have to ask ourselves that there is so much difference between yi and y bar, and one represents the other. Why the difference? How can you explain this difference? Right? So, because these differences can be positive or negative, there is no harm in squaring and adding the differences, because we have a lot of y values and there is a y bar. So we want to have a measure of all such distances. Then we have to see not only one difference, but all the differences, and we have to square them. And why we are squaring them, we have talked a lot about it. The same reason why we squared ui hat, why we squared ui hat, and why we added them, right? So that's the reason why we are squaring yi minus y bar also and adding them, right? So we are doing the same thing for all these. We are taking all the yi's, subtracting y bar from all the yi's, squaring them and adding them. So
So
this
that
is
they
some,
are so the reason for doing this is so that they are unidirectional and there are no negative values.
yes, the same reason that we had for ui hat, right?
But the same
So
reason why we are doing all of it, like why
yes, yes.
OLS method is made.
Yes, yes, yes. The same reason is there. That's why we square it, and then we added, and we had one full class on just explaining why do we square it and why do we add these. We don't have that recording. That would have been great for you, but still we spent a lot of time in class doing that because we were face to face at that time. It would have been great if you had the recording of that also. Anyways, just try and remember that that's the reason why we square and add this quantity also, right? So this is some quantity and we are interested in this quantity. Keep it in mind, yi minus y bar, right? And I will give it a name. I'll say this is total sum of squares. Total sum of squares. This is a quantity known popularly by this name, total sum of. So let me write a short form here, TSS, total sum of squares. So why is it called total sum of squares? Because it's a square, because it's a sum. And why total? Total means, the meaning of total is total variation in y that needs to be explained. Total variation in y that needs to be explained. You can see that all of these are differences, yi minus y bar. So we are talking about some sort of variation in y, right? How much y is varying as compared to the mean, right? How far the y's are from the mean, how far each of the y is from their mean. And that means we are talking about how much variation is there in y around the mean. So this is the total variation which is there to be explained by the regression. That's why we are doing a regression. We want to explain this variation, right? We are doing this regression to explain this variation yi minus y bar, summation yi minus y bar squared. So we call it total sum of squares, right? Now, let us take another point. Now see this part. Let me remove the yi minus y hat y bar part so that my graph is not overpopulated. What about this quantity? This is y hat minus y bar. Yi hat minus y bar. Let me write it here. And let me square it and sum it as we did for others. And we call it explained sum of squares. The word explained means that out of yi minus y bar, y hat minus y bar is explained part, right? So out of yi minus y bar, it has two parts. One is yi minus y hat, another is yi hat minus y bar. This is the part which has been explained by regression. And this is the part which has not been explained by regression, and it is written here at the top, that is the residual. And I will square it and I will sum it and I will call it RSS, where R means residual. So this is residual sum of squares. This is total sum of squares. This is explained sum of squares. There are three things here. You can see in this explanation that yi minus y bar has two parts. In the graph also you can see yi minus y bar is made up of two parts. Y hat minus y bar plus yi minus y hat, right? These two parts are there. This lower part has been explained by regression. So how can I say that this is explained by regression? Because regression line is passing through this point, and whatever is below the regression line and above the mean has already been taken care of. It has been explained by regression. So this y hat minus y bar part has been explained by regression. And what is not explained by regression is the above part, y hat, yi minus y hat. We call it RSS, residual sum of squares, if we square it and sum it. So there are three important quantities. One is RSS, one is TSS, and one is ESS, right? Now, TSS is equal to ESS plus RSS. How can you explain this equation? Simply because total sum of squares is the total variation which is there to be explained. ESS is the explained sum of squares. That means this is the part of TSS which has been explained. What remains to be explained is RSS. That's the residual sum of squares. This residual sum of squares is also written as summation ui hat squared, because ui hat is equal to yi minus y hat, so that we get this expression for RSS, which is written at the top, right? Whatever is there inside the parenthesis in the top equation, the equation for RSS, is nothing but the residual yi minus y hat, right? So these three quantities are important, and this equation is important, that TSS is equal to ESS plus RSS. It's a statistical fact, right? Because we have defined these three in such a way that ESS plus RSS is equal to TSS, right? Coming from here,
Uh,
yeah.
Sir, I got it, but I want to know, like, like I got it individually, but how is that signifying R square?
Okay, I'm coming to that point only. I'm coming to that. I'm just building up the basic notation for you,
Oh, all
because
right, sir.
if you know the notation, I don't have to explain anything. You will see the notation and you will understand. So I'm building the notation so that in future, when I'm writing something, then I don't have to explain it that much because you already know it. So that's why I'm building this basic structure. What is meant by what, right? So now that you understand RSS, ESS, TSS, I will be referring to these as they are now because you should learn these definitions, and I will not go into the details of it. I'll just say TSS and you will understand what is TSS, what I am referring to.
So actually, we have our next class right now. So can we please take it up in the next class?
Okay, I'll take it up in next class, but I'll take just 2 minutes to explain this equation, right? Is it okay or should I leave it?
Sir, that's totally fine.
Okay. So I have explained RSS, TSS, and ESS. If you divide this by TSS, you get this equation, right? And this is R squared. So R squared is what part of TSS is explained by regression. Suppose TSS was 6 and ESS was 3. So it means R squared is 0.5. So you would say that 50% of TSS was explained by the regression, right? So that's where R square comes into the picture. Of course, we have to understand all these things, so we will do it tomorrow, right? So let us stop here. If you have any question, you can ask.
Oh, no, sir. Thank you. Also, sir, could you please share the previous recordings with us?
I will share the recordings with you. I will upload it on the Google Classroom.
Thank you.
Please send me the attendance also.
Yes, sir. I'll just record.